Yesterday we let's summarize some of the rules that we have come up with and some observations. So we said that again, we showed that if f is increasing, then f prime is positive. If f is decreasing, then f prime is negative. And we also said that if f is constant, then the derivative is 0, right? We actually showed all three of those things. So this is somewhat related to some of the problems on the homework. We also, while we're here, found that if f of x is equal to a power of x, then the derivative is nx to the n minus 1. We've shown all those things so far. So as you've been going through the homework, there's a lot of difference quotient stuff, too much in a lot of ways, a lot of tedious plugging in. We won't really be doing that approximation that much anymore. But there are some problems about graphs, and so I wanted to talk about them. All right, so I'm going to put in a function in here. Let me put this function in here. Let's see if it's nice enough. Oh, I like that. I like that. And then I'm going to do this, maybe. Okay, and then I want to do, let's do this. There's that. So I'm putting in a function, and then I'm going to put in another function. Let's do this. Perfect. All right. Two functions. One function is the derivative of the other one. One of these functions is the derivative of the other function. Right? So which one is the original function and which one is the derivative? Go ahead.
The green one is the original.
Because?
Because it's x to the fourth function, and then if you apply the power rule, you get 4x to the thirds, and that's what the orange one is.
Okay. I like that. Other reasons? Go ahead.
When the original function is decreasing, the derivative function is.
I'm sorry, say that again? When the
original function is decreasing, the derivative graph and the derivative is negative.
So and therefore what, go ahead. So have you chosen, so which is which?
The orange one is the derivative.
The orange one is the derivative, and this is, so you're saying that when this is decreasing, whenever this is decreasing, the orange graph is negative, and
when the original graph is increasing, the derivative graph will
when this starts increasing. So yeah, we can zoom in a little bit, as you might expect. I prefer that answer, right? And there are a number of reasons. One, because I may not have put a polynomial of degree 4 here. This may be some other function, right? And also that reasoning is in line with what we just wrote, right? And so that is the reasoning that I prefer, right? That when the green graph is decreasing, the orange graph is increasing. The orange graph is negative. When the green graph starts increasing, the orange graph is positive. And then the final case, when the green graph is no. What's the other case? What's this point?
a point of inflection.
No. When it's flat or when it's constant, what is the orange graph? Zero. Right? So that is all in line with this remark here. Right? Please.
Oh, never mind. I was going to say the one income is the x to the fourth, right?
Say it again?
Is the one income x to the fourth?
It happens to be in this case. That's right. That's right. Why would you say that? Why did you say it was x to the fourth?
Just the W pattern.
The W pattern, right? Is that the reason? Okay, excellent. Of course, yeah, we could have put anything in there, right? Please.
So the green graph is the original. So
The green graph is the original graph.
I thought it looked like it's decreasing.
Say it again.
It looks like the green graph is decreasing from whatever there to negative 1.07. Yeah.
Looks like it's decreasing from where?
From I guess negative infinity to negative 1.07.
Yeah.
It looks like the derivative negative in all those parts because like at the maximum it looks like it's like going before negative 1 looks like it's
Are you saying these don't look like they line up?
oh wait, I can't see that well. Never mind.
Yeah, I mean, no, it's a great question, right? So, but this is just scale and like maybe an optical illusion, right? But they are right over top of each other.
Okay.
Yeah. Thank you. Any questions about this? I don't think they're going to give me different colors. We'll see. One function is the derivative of the other. Okay.
I think orange is the original function
Because?
because when the orange function hits the constant factor at 0.0.
I'm sorry, say that again?
So when the orange graph hits its constant or its maximum at 0.1, the green graph crosses the x-axis.
So when the orange graph is flat, the green graph is 0.
Yeah.
Okay, go ahead.
And when the green graph is increasing, like from like -2 to 0.
When the green graph is increasing.
When the orange graph is increasing.
When the orange graph is increasing.
-2 to 0.
From -2 to 0. When the orange graph is increasing.
Or from -1 to 0.
When the orange graph is increasing from -1 to 0, go ahead.
Oh, wait. Never mind.
Oh. Okay. One is the function and the other one is the derivative. No one's calling out what this function is? Sine. Okay, great. I was about to say, you can call out x to the fourth. I don't think I can call out x to the fourth.
Well,
Go ahead.
the orange function is the sine of x, and I mean, I guess I just know that the derivative of sine x is cosine x, which is the
Yes. And this is excellent. You present a great challenge to me, right? Because you go directly there, and it's all of this stuff in between me putting up that graph and you saying what you just said, right? The great challenge that we all have in this classroom for people who have had it and know that is that there are tons of things, so that when I ask you that, and this is to everybody, that there are some conceptual things that I want you to say about this, right? And then finding that middle ground, because again, if you go out knowing that that looks like sine, I cannot wait to put in the outrageous function I'm about to put in just a second and see if you can call it out. Because it is not about whether you can call out the function. It's about whether you understand which is the derivative of which, right? In one moment. So we need to focus on the concepts and not on just knowing the answer. And again, this is a great problem to have, right? That a number of you already understand a bunch of the big picture stuff, but I'm asking you to step back and get these concepts, right? And explain it so this is the way that we know what it is, right? So everyone seems to be playing the video game and you already know all the shortcuts. Like you're playing, oh God, I don't even know what video to reference for you now. Video game. You're playing Mario and you're already, cutting through everything the first time, right? And that's okay. But you may be missing out on all the coins, right? So I'm going to end this metaphor now. Okay. Yeah. No, again, it feels like a game show. This is sine and cosine, right? But which is which?
Cosine is.
Go ahead.
The green graph is the original and the orange is the derivative.
The green, and what graph is the green graph?
It could either be sine or cosine.
Tell me which one it is.
Sine.
Is that right? Okay, good. Okay, how do you know the green graph is sine?
It starts at the oscillation line.
Say it again.
It starts at the oscillation line.
What's the oscillation line?
The midline is 0. Like
The y-axis.
yeah.
This line right here?
No, like the x-axis. It's like the oscillation line, like the midline.
Oh, the midline. Okay, I just not heard that terminology before. Okay, so it starts at 0, 0?
Yeah, sine.
Sine starts at the origin.
Yeah.
Okay. Other reasons? Go ahead.
But it could also be moved. It could be translated so that it can look like sine, but it actually is cosine. So we don't really know which is which.
You don't know. Okay, that's interesting. Okay, so
Cosine can be translated so that it looks like sine. Like the orange graph can be translated just enough to look like sine.
So you mean I can move this over here?
Yeah.
But if I did, would it be the same function?
Yes, it would.
Oh, this is good. Okay, so let's go back. So, all right, let's clarify some things.
Like you just don't know which one is which.
Okay, good. So we're good. We need a definition. So, all right. So, and as you know, I have a 6-year-old, and whew, the greatest honor of my life is to be a father to that person. Oh my God, right? And I never thought that joy in my life would come from serving another person, and that finding my purpose would be sitting around somebody else, right? In the process of helping, teaching, and learning from her, it's gotten to the point where she'll say, she'll do something bad, and I'll say, oh, this is good. She's like, oh God, so you've already learned that, right? All right, so suppose I had f of x is equal to x plus 3, right? All right. There's x plus 3. I'm going to tell you something about g. I'm going to tell you that g of x, oh no, I'm not even going to tell you what g of x is. I'm going to tell you one value of g of x. I'm going to tell you that g of 1 is 7. I'm going to tell you that h of x is x plus 3. And these are defined, all of these functions are defined on the whole real line. Okay. I have some questions for you. Is f equal to h?
Yes.
Are f and h the same function?
Yes.
Yes? Why? Why are they the same function?
For every x value, you get the same y value.
That's exactly right. For each x in the domain, f of x is equal to h of x. When x is 5, f is 8, h is 8. When x is negative 3, f is 0, h is 0. For every x in the domain, they're the same. That's what it means for two functions to be equal. For every value in the domain, they're the same. The question is, could f be equal to g? I told you one value. Could f be equal to g? What does it mean for two functions to be the same?
Every value.
For every value. What's f of 1?
4.
Could f and g be equal?
No.
Absolutely not. Absolutely not. Is that okay? Sine is a function, yes? Well defined. What's the value of sine at 0?
0.
0. The value of sine at 0 is 0. Could sine be the orange graph? The value of sine goes to the origin. Yes? Could sine be the orange graph? No. The orange graph could not be sine. Sine goes through the origin. Are there questions about that? Sine goes through the origin. Any function that doesn't go through the origin could not be sine. Sine is uniquely defined. Is that okay? Yes. Questions, please. Go ahead.
Like he was saying, though, can't you shift it so that way? Are we just assuming
Yeah.
that it's just sine of x, not like manipulated so that or like the cosine could be shifted to the right, so that way it goes to the original x line?
Do it. Yeah, we're talking about the sine of x. It's the sine of x. Yeah.
Right. It's not like 2 sine x or like sine x squared or anything.
No, we said it's the sine of x.
Oh.
It's the sine of x. Yeah.
Okay.
Yeah.
Could
Go ahead.
you also just say that because sine is an odd function and then theorize that the sine function crosses through 0 is no origin?
We can say that. Yeah. Yeah. So, and indeed, we can shift this. How many units? What's this distance? Pi over 2. Excellent. And if we shifted this distance, what would this become?
Green.
It would become sine. That's right. It would be sine. Right. So it would change. Okay. So yes, the green graph is the sine of x. Okay. All right. Great. Questions about this? All right. Oh, last one we'll do. Oh my God, I love this class. X. Yes.
So does that mean that cosine x and sine of x are derivatives of each other?
The derivative of sine is cosine. The derivative of sine is cosine. We'll have to verify that. Yeah, so let's go ahead and I want to do this. Let's see what we got here. I want to... Oh, this is fine. we'll leave it here like this. Let's move this out of the way. All right. One function is the derivative of the other. Go ahead. Go ahead. The blue graph is the derivative of the red graph. Redemption. Oh, are you going to tell me what function this is? No, and you can if you want. Right? Tell me why.
From negative infinity to -2, the red graph is decreasing. And wait.
Help them out. Go ahead.
I think that the red graph is derivative.
The red graph is f, and the blue graph is the derivative. Is that what you're saying?
It says the blue graph is the original.
Oh, the blue graph is the original. Okay, I'm sorry.
No.
Okay, because?
Because when when the blue graph is constant, so like the maximum, there's a zero.
The blue graph is flat.
Has a 0.
Okay.
So like at -2, for example, and then for when the blue graph is increasing, so like negative, well, I can just assume it's negative infinity to about -2, I would say. The derivative, which is the red graph, is above the x-axis, so f prime is greater than 0. And then you can say the same from -2 to 0.
Right.
Which on the original, the red graph is less than 0.
Other comments about that? Go ahead.
The blue graph is like x6 and the red graph is x2.
Let's say that again.
Right? The blue graph is like
Oh, you want me to zoom out?
Yeah.
Oh my god.
Yeah.
Okay, I'm like,
it looks smaller.
Well, obviously this graph is right.
It looked like there was less zeros. So
There are infinitely many zeros. They're
never
infinitely.
mind.
Oh, never mind?
Never mind.
Yeah, and that's what I mean. The difference between those two things. That's all that I mean about where we're trying to get, right? That, if in the case we cannot go ahead and just call out what the function is, can we still go ahead and give the reason, right? So, the blue graph, right? So when we're talking about the function, let's talk about language. Math is a language. When we're talking about the function, we're talking about increasing and decreasing. When we're talking about the derivative, we're talking about what? Positive and negative. Right? So in this context, we really don't care about whether f is positive or negative. We don't care about whether f prime is increasing or decreasing yet. We care about whether f is increasing or decreasing or flat, or whether f prime is positive, negative, or 0 respectively. Yeah.
When like for the blue graph, how it there's like the minimum at 0, like
Yeah.
relative minimum at 0. Usually when there's a minimum on the x-axis, does that mean that there would be like 2 x's for that?
There would be 2 what?
X's? Like does that count like 2 zeros?
2
Roots.
2 roots.
When it bounces
Like
off the
I know like for an x cubed graph, there's
Yeah.
3 zeros.
Yeah.
So for like if there was a minimum or maximum at 0, is that usually like that counts for 2 because 0 is 2?
Oh, I see. So okay, so this is good. So you're talking about a polynomial.
Yeah.
Right. So this is not a polynomial. Oh, is this a polynomial?
No, it's not.
How do you know?
Because it keeps oscillating.
Right, because it hits the x-axis infinitely many times. Right, so this is not a polynomial. So this is also good. I did not know we were addicted to polynomials. I did not know that. No. I've already, no, it's not just you, sister. I've already gotten this already, that people love polynomials. And they are great because you can do tons of examples. But that's why I had to do this one. I mean, this is great because I was just doing like I was putting some problems up and people just start calling out the function. This is great. So go ahead.
Just out of curiosity, what is it?
Oh, that's a great question. That's a great question.
That's
That's a great question. So,
Would you like to try to like tell us the function?
no, we're going to talk about it in just a second. Let me answer your question. Go ahead.
Oh, no.
Oh, you want to, like, what is it, right? Absolutely. So this is good. So, and this is actually good. So I'm going to get rid of one of these, right? So it is, let's summarize, first of all, that the blue graph is the original graph, and we are asking about a relationship between when the blue graph is increasing or decreasing, that the red graph, if it is the derivative, should be above the x-axis whenever the blue graph is going up. It should be below the x-axis whenever the blue graph is going down. And whenever the blue graph is flat, then the red graph should be crossing the x-axis at the same point. I'm going to open the floor to any questions about that explanation. That again, when f is increasing, f prime is positive. When f is decreasing, f prime is negative. When f is flat, f prime is 0. We proved that last time. Half of that is extra credit. And here is an example of that. Please.
So when people say like negative infinity to 0, it's overall decreasing. Is it just because?
Okay, so this is also good. So when you say it.
Oh, sorry. The blue graph.
The Google. So f is
Function.
Yeah, f is overall decreasing. You say?
Yeah. Is when people say that, does it mean like from like say negative? No. So like just because, how do they know it's overall decreasing? Because I see points when it's increasing and points when it's.
I don't know who would say that f was decreasing overall. I just don't know. That doesn't fit our definition of decreasing, right? For f to be decreasing, that means if I give you any x, right,
Yeah.
and any y, then f of x is always less than f of y, and that is not true for this function, right? So no mathematician would say that the blue graph is decreasing.
All right.
Yeah, no mathematician would do that. Excellent. Let me get rid of the red graph. There's the blue graph. We want to know what this is. Oh. Great. Okay. So, guesses? Partly, it should probably have what? I multiply two functions. I'm going to tell you it's a product of two functions. It's a product of two functions. And so it's oscillating, so that means it's probably a sine or cosine.
Cosine.
You think it's cosine? Okay. And then it looks like, what does this look like?
It looks like a parabola.
It looks like a parabola. Okay. That kind of gives it away. It looks like so when you want to figure out what a function is, you want to look at all parts of it, all parts of the domain, right? So you want to look at what happens on the whole real line. So you want to look at what happens all the way to the left, all the way to the right. But you also want to look at what happens around 0. Okay. Now around 0, it looks like a parabola, right? And we know that it involves either sine or cosine. What do we know about sine around 0? What does it look like? So we're gonna say this earlier. And we're gonna say this later, I should say. That when you I want to make a comment about sine. Wait, is the blue graph sine or cosine? Sine. What's that line here? This is y equals x. It is the tangent line. Y equals x is the tangent line. We'll demonstrate that next week, maybe. That the tangent line to 0 of sine is x. Sine and x are nearly the same around this point. Okay, we'll show that. And that's the other way to know the difference between sine and cosine. That sine looks like x. Sine and x are identical at 0. Any trig function that looks like x at the origin has to be a sine factor. Okay, so if that's the case, what would happen if I look at x times sine x around the origin? It would really look like x times x. It would really look like x times x. So x times x is a parabola. So I have graphed x, the sine of x. It's x, the sine of x. So I took this one and I multiplied it by this one. Right? So again, that's why it looks like a parabola early on, because around here it's like x squared. And then where are all these oscillations coming from? And why are they getting bigger and bigger? What in the world's going on there? X is getting bigger and bigger, and sine keeps oscillating, positive and negative. X is getting higher and higher, and sine is like, no, we got to change the sign. I'm going to -1. But the x is like, well, wait, I'm going up. X is going all the way up. Sine wants to be negative. That means it's got to go down. And then sine goes back to be positive, but x just keeps going up, right? So we see what's happening here, right? So that if I put x here, this is just following that. And of course, it's also following that, right? So it just oscillates. If sine oscillates between what two numbers? Sine oscillates between -1 and 1. And so x sine x should oscillate between -x and x. Okay. Odd. This is odd. X is odd. Sine is odd. The product of an odd function and an odd function is even. So this is symmetric with respect to the y-axis. Okay. Okay, good. Excellent, excellent, excellent. Massive detour, but that is all good. I'm going to take any other questions about the homework. Right? So the homework involves some difference quotient stuff. It also involves some looking at the graphs. There are some things we took out about inflection points because we haven't talked about them yet. Go ahead.
On the homework, I was able to change the questioning to get it right, but it asked for the interchange rate of change at 3. They didn't give you a 4.
They didn't give you what?
Like the graph only went from x equals 0 to 3.
Yeah.
That's an interchange rate of change.
Yeah. They probably asked you just to estimate it.
Yeah, so that's to estimate it.
Yeah.
But I didn't really know
I hate those questions.
Yeah.
Yeah, no. So how do we do that?
I had to click the summary question, and it gave you another round.
Oh, okay. Did you? Okay. Yeah. So I probably wanted to take that one out too, because basically all you're doing, the problem with that estimating is not a problem. Is that the problem is that when you estimate it, you might get 1, someone else might get 1.1, someone else might get 1/2. Estimation is just so subjective. So I apologize for that. There shouldn't be that many more estimation questions. Go ahead.
And also, the very last one about something about inflection.
I've removed that one.
Yeah.
Yeah, we'll talk about an inflection point in a few weeks, if not earlier. Okay. Other questions about the homework? Please.
For one of the questions I was doing, I think I oversimplified and said the answer was wrong, so I put in like a previous step and it said it was right. I don't know if I mapped this up or if it was like.
I'll need to see exactly what it is. Yeah, so just show me. You can show me after class, and I'll take a look at it. Yeah, please.
There was a question on there. I wasn't too sure. It looked like it was like a definition, but it didn't have like the limit.
Oh, right. So yeah, you just leave it in terms of h.
Oh, okay.
Yeah, if there's no limit, then don't make h0 at the end, right? So whatever function you get, just leave it in terms of that and put that in. Yeah. Please.
There are questions that when you're looking at a graph, you have to really work on that.
I don't think so. I can certainly let Jessica know if she wants to look at your notes that she should not be looking for work on those problems. Thank you. Please.
Yesterday I explained number 6 with like the tickets, but I went back and did it, and
With the tickets?
the raffle tickets.
The raffle tickets?
Oh, the 100 meter tickets. I figured it out.
It was where we gave you. We were supposed to find.
Give you a table.
Oh, it didn't like.
No, I got the answer.
I got the answer.
Well, how are you supposed to do it?
You just average the one before it and the one below it. And average it.
That's not what we said?
That's what they said. Yeah.
You find minus the last.
Did it not work? It did work. Okay, so your question was.
F1 didn't give me one after.
It didn't give you one after.
Oh yeah, I got the most bottom one, so I just did that one and the most before it.
So, okay. So let's rectify this. So, okay, let's bring it up. So it wasn't this. It was it 2.2? What number?
Like number 6.
Number 6? So the numbers are slightly different now, right?
They change every single time.
Yeah.
Mine asked for D.
105, we did 91 and 119, and you say you ran into a problem with what?
It gave me the last one.
Oh, it gave you the last
Oh
one.
yeah, that's a 92.
Oh, and so what did you do?
I didn't know.
So just use that one and the one before it.
Just these two?
Similar problem.
Just do these two. Oh, just keep trying a similar problem until you get it in the minute. Okay, this is good. So, you could certainly do that and cheat the system. Yeah, you can certainly do that. But yeah, no. Did you try just the last two?
I think so.
Okay. Yeah, and again, we won't be running into these types of problems of estimating. By the way, there is no right answer to this in a lot of ways, right? This is just a fascist question in the sense that it's saying estimate the way I want you to estimate, right? That's crazy. Okay, so yeah, so again, we're running into issues with the word estimate. So depending upon the form of it, there are all sorts of ways of estimating the derivative. But in general, again, as we said last time, if the data is smooth enough or doesn't look oscillatory, then you should just pick around it. And yeah, I'm surprised they actually gave you the last one. I may actually write the author about that. So what happens when you ask for an explanation? Does it give you explanations? Hints? No. Okay. So just okay. Some of them. Okay. That's what I was wondering. I'm sorry. 15.
Which is the one where I think I went too far or something.
15. Okay. So good. This would be helpful.
I'm not sure if it was just me or if it was the system because I did it twice.
Yeah.
2 different problems.
All right. So this is called the difference quotient. Right. So this is just going to involve some algebra, right? So it's g of minus 1 plus h is equal to 3 over minus 1 plus h minus 3. And the other problem with this is that, let's simplify this while we're here. This is 3 over h minus 4. The other problem with this is that who knows how far it wants you to simplify, right? I mean, that's another issue, which is why, again, I don't like giving these. Or I'm happy to be done with these very soon. That's g of minus 1. And so then g of minus 1 plus h minus g of minus 1 all over h is equal to 3 over h minus 4 plus 3 over 4 all over h, right? Is that okay?
Yeah.
Okay.
Then you multiply the 3 over h minus 4 by 4.
The 3 over h minus, yeah, right. So then common denominator, 4 times h minus 4, and we're talking about 12 plus 3h minus 12 all over h, right? Is equal to 3h over 4 times h minus 4 all over 4, and that, I'm sorry, all over h, thank you, all over h. The h's cancel. 3 over 4 times h minus 4. And you didn't put this in?
Yeah.
Or something equivalent to that? It didn't like that? Let's make sure we read the directions correctly here, because I'm really liking that.
It's so simplified. I put in one that wasn't completely simplified and not more simplified.
It likes that. Oh, it distributes. But I would be surprised if it didn't take this. But this is something, yeah, so we have the same thing, right?
You just forgot a negative.
I'm sorry?
You forgot a negative, because when you did g of negative 1, we wrote down 3 over 4 instead of 3 over negative 4.
3 over 4?
Yeah.
Oh, this is negative, right?
What other one?
Well, we were already subtracting.
Oh, I see what you mean.
Yeah, but let's just make sure. No, that's all right. No, so that all matches up, actually. So I don't need this negative. So they have negative 3 over 16 minus 4h, right? So negative 3 over 16 minus 4h is,
Same thing.
it is the same thing, right? Yeah. So yeah, I would be surprised if it, and I wonder if I can test it here. I would be surprised.
Yeah.
It is switched on the bottom, but then they have a minus sign in the numerator.
No, but even that shouldn't be a negative.
Okay, so this is minus 3. Let's go ahead and show this. So negative 3 over 16 minus 4h is equal to negative 3 times negative 4 times negative 4 plus h, which is equal to 3 over negative 4 plus h, which is equal to 3. I'm sorry, there's a 4 here, right? 3 over 4 times h minus 4.
The question is, if the answer was 3 over 4, shouldn't
Wait, go ahead.
it's because like when you got your answer there in the box, it's 3 over 4 times h minus 4.
Yeah.
You distribute that 4, there shouldn't be a negative magically. That's what I'm asking where you got the negative from.
Which negative?
The one in the answer you got in the box.
What, this negative?
No, because I know when you distribute, it's going to end up being 3 over 4h minus 16.
4h minus 16, that's right.
Negative 1, it ends up being the same. So negative 3 over 16 minus 4h is the same thing as 3 over 4 times h minus 4.
So 3 over 4h minus 16 and negative 3 over 16 minus 4h, they're equal, right? So they just factored out a negative and they cancel? Yeah, so negative, this is negative 3 over negative 4h minus 16.
Okay. Oh,
the point is that no matter what, they should mark it right.
Yeah, that's super bizarre.
So if I put in, what did we have? We had 3 over
3 over 4 times h minus 4.
4 times h minus 4.
Oh.
That?
Another parenthesis.
You gotta add that in parentheses.
Thank you.
I don't know if you can.
The syntax is okay?
Yeah, I can check it on my computer.
Yeah, check, yeah. But you tried to put that in and mark that wrong?
No,
No.
I had different numbers, but the final answer, like I put it in and it kept saying it was wrong. So I put
Okay,
in, like,
I'll just take a look at it. Yeah. And again, that's something that you can just let me know about that. Here's the deal. We're dealing with software, so it's going to be buggy, maybe. So we're going to mark, if stuff is right, we're going to mark it right and give you credit. It's just that simple. Okay. Okay, excellent. So Jessica's going to be there tonight, 6 to 6:30 to 9, right? Grinding away with you if you need help. Excellent. All right. We're going to have some derivative rules now. We have a couple already. If f of x is equal to c for every x on the real line, then the derivative is 0. And if f of x is equal to x to the n, and that means that f prime of x is nx to the n minus 1. And now we're going to do our product. F of x times g of x, brand new function, h of x. I'm going to take the derivative of that. All right. Okay. It's called the product rule. H prime of x is equal to f prime of x times g of x times what?
X.
G prime of x plus what?
G prime of x times f of x.
G prime of x times f of x. Please.
Does it matter which order those are?
No, because addition's commutative. Yeah, it doesn't matter the order. Okay. So we'll do some applications at some point with the derivative to word problems and stuff like this. Specifically, we'll say, well, we've been doing this from the beginning, right? That if I am driving down the toll road, right, and if I had a function that represented my position, then the derivative represented the what? The rate at which my position changes, right? We have a name for that. The velocity, right? Okay. So that if at any time I give you my mileage, then the derivative gave me the rate at which my mileage changed per unit of time, right? So if I'm driving and I'm going and I'm at mile marker 20, right, and I got there in some amount of time, then you can calculate my average velocity in miles per unit of time, right? So that if the original function was if you put in time and it comes out hours, then the derivative is in miles per hour, right? If you put in time and it gives you miles, then it's in miles per hour. Okay. I bring this up only because some people want to write that f prime is h prime is f prime g prime, and oh my goodness, no way in the world that could be true, right? From the example that we just talked about, that if it is the case that h People who write, I want to be clear, and I say this with love, of course, people who write this have no idea what they're doing. It's just that simple. Hopefully, if I call you out like that with love, you'll never do it. And you'll be committed to understanding what things are, right? So that if h is a function that we talked about that takes time to miles, then h prime should be what? In what units? Miles per time, right? So that if f and g, let's suppose f and g were in the same units, okay? So suppose f took time to miles and g took time to miles. What does fg do? It takes time to what? To miles squared. Questions on that? Because it's just miles times miles, right? And therefore, when we do the derivative of f times g, what are the units? Say it again. Miles squared per time. Those are the units that you need to have. Why can't that be this? What are the units of that?
Miles squared over time squared.
Miles squared over time squared. It's miles per time times miles per time. The units are not the same. And oh my goodness, if my physics brother would dare do this, I would faint, right? That there's no way that we should make those the same simply based on the units. So that whatever the derivative of f times g is, it better be miles squared per time. And this just so happens to fit that. This is miles per time times miles, which is miles squared per time. And this is the same thing, and then you can add them. Okay. Now the street version says this. Look, I have f and I have g. I'm going to multiply them, and I want to know how that changes. Well, the rate at which f times g changes, it has to have something to do with f. It better have something to do with g, and it better have something to do with how both f and g change. So that if I care about how f and g changes as a product, then f better be there, g better be there, and the rates at which each one changes better be there, right? I need f, I need g, I need f prime, and I need g prime, right? So if you realize you need all four of those things, and then you think about the units, what else could it be but that, right? That f and g are interacting through multiplication, that the rate at which they change should probably be another interaction between the rate at which f changes and what g is, and the rate at which g changes and what f is. And in some sense, it only makes sense to add. Right? So that's the street version. Right? We're going to prove this in just a moment. Right? But I'll open the floor to questions about the product rule. Please.
How do you put the units for FG prime?
Oh, good. So fg prime. So fg takes time to miles squared, because f takes time to miles, g takes time to miles, and so f and g have the same domain, and so f times g is going to have the same domain. But then if I take miles times miles, it's miles squared. Is that okay? Yeah. And so that's the domain of fg, and this is the range. And therefore the derivative is always the range per the domain. The range per the domain. Excellent. Something else about this? Okay, good.
The derivative is range over domain.
Oh, for sure. And yeah, for sure. You as a physicist, for sure. You'll see the derivative the rest of your life, player. All right, so claim. The derivative of f times g is f prime g plus g prime f. I'm going to do this one, and then we're going to do a quotient rule, and I'm going to give that one for the proof of that for a ton of extra credit. That's going to be fun. Here's the proof. I haven't really defined what a proof is, but a proof is a list of statements all starting from what we suppose to the conclusion that we want, right? So H is a bad letter with the definition I'm about to use. Let's call it P. Let P of X equal F of X times G of X. And I'm interested in the derivative of P. So P prime of X is equal to, we know what this is, it's the limit as H tends to 0 of P of X plus H minus P of X all over H. Whatever I'm about to write a ton of equal signs, and whatever I write, it better be a fact, and that my last statement that I write is F prime of X times G of X plus G prime of X times F of X, right? That's going to be the last statement. This is equal to, well, P of X is F of X times G of X. What's P of X plus H? It's F of X plus H times G of X plus H. Minus P of X is F of X times G of X. And this is all over H. All right. This is equal to the limit as H tends to 0 of F of X plus H times G of X plus H minus F of X, G of X, all over H. Right. I'm going to pull some math magic here. I'm going to introduce a new term. I'll put it in red. And it's going to be minus F of X, G of X. Oh, let me do this. Let's do F of X. Let's do G of X plus H. I'm going to put that there. This thing is bugging out right now. Oh, maybe I need to turn this up. Now, I can't just subtract that off without adding it back, right? So then, to make sure I have not changed anything, F of X, G of X plus H. So now this is equal to, so now what I'm going to do is I'm going to split these in half. This is equal to the limit as H tends to 0 of F of X plus H times G of X plus H. And now I'll bring the red part over here with this. Divide that off, and then I'm going to put this green part over here with this. So I've just split them off like this. So again, it looks like math magic, but somebody figured this out many decades ago. And this helps with the proof to introduce this. There would be no real way to be able to know how to do this. So this is equal to, What do these both have in common? G of x plus h, and we'll factor it out. This is the limit as h tends to 0 of g of x plus h times what's left? F of x plus h minus f of x all over h. And then this one, what do they both have in common? F of x. We'll factor that out. F of x times g of x plus h minus g of x all over h. We're ready to apply the limit. As h tends to 0, what happens to g of x plus h? What is it? It is g of x. How do you know? Because g is, what do we know about g? If I'm taking a derivative of it, it's certainly continuous. Right? So it should be the case that the limit as h goes to 0 of g of x plus h should be equal to g of x. That's what continuity means. Right? So that's because g is continuous, because g has a derivative, and we need to talk about that in a second. And oh my goodness, what does this go to as h goes to 0? What's the limit as h goes to 0 of f of x plus h minus f of x over h?
F of h.
But yeah, I'm with that.
It is f prime of x, and whew, thank goodness someone saved us today. That's the derivative, right? Okay. Plus, that f of x is just hanging out, and then this one right here, what's that? That's g prime, and that is the end of the proof. That's what I wanted to show. That if I have f of x, g of x, and I look at the derivative is g times f prime plus f times g prime, not because we said so, because we just proved it. Please.
On the equation, on the top.
Here?
On the top.
At the top.
Yeah, that one with the red. Why did you subtract and add those values?
Because it was convenient.
You just
Right.
leave that off the top of your head.
Yes, that's correct. Right. So somebody, and I wish I could take credit for it. I would probably have a lot more money. But someone a long time ago. So what happens with mathematicians is that they try to figure stuff out. We're a big community. Some person, he or she, was trying to figure out a rule and said, "Oh, I can do this," and then we've been copying it for decades. Right. So some proofs have no useful lessons from them, and so this is what I mean by it's like magic. Somebody figured it out, and you saw that you can do it. It's mathematically legal, but I would never expect anybody to just be like, "Oh, I need to add and subtract this thing." Right. So this is not something I would ask on the test. But again, what I'm trying to hammer home is that trying to break this notion that mathematics is something that you get just because some person stood in front of you in your classroom and told you this is the rule, remember it. It is every mathematical statement ever can be proven, or we just accept it, right? So there's some basic rules that we accept, and then from that we can prove. We call those statements axioms that everybody agrees upon, and then from that we prove everything else. And so the biggest example of this is Euclid. So Euclid gave 5 axioms, and he says from these axioms, all of geometry we can create, right? So you all have had geometry. So he said, look, there's a point. Then he said, look, a line is 2 points when you connect them that extends indefinitely. And then he says that if I give you a point and a line, and that point is not on that line, then there's one and only one line that goes through that point. And then he gave 2 other statements. And from that, he proved SAS. He proved everything in Euclidean geometry is just all derivable from those 5 things, right? And so that's what mathematics is about. Every statement that I have, the product rule, or the quotient rule we're about to do, it's not just because let me just tell you what this is. That's true because there is some proof behind it, right? That's the point. Okay, great. So let's put this in practice. There'll be a ton of these using the product rule. So we've just shown that the derivative of fg is f prime g plus g prime f. And that means we can take the derivative of x squared plus 6x times 3x plus 5. We can do this in a couple of ways. We could FOIL this out and take the derivative individually, or we can use the product rule. And let's go ahead and do both. That's h of x. Let's FOIL first. Then it's x squared times 3x, so 3x to the third
Plus
plus
5x
5x squared
plus 18x squared
18x squared
30x
plus
30x
30x 3x cubed plus 23x squared plus 30x. This is still h of x. Sometimes we do simplification and we think we've taken the derivative. We have not. The derivative of that, this is the notation for the derivative, power rule, is 3 times the derivative of x to the third is 3x squared plus 23 times 2x plus 30 times the derivative of x, which is 1. I won't be writing it out this way forever. I'm going to be going much quicker. I'm sorry?
We go straight to like the end.
You can. Yeah, I can because I'm teaching. So this is equal to 9x squared plus 46x plus 30. That is the derivative of h. If we wanted to use the product rule instead,
Could we assign like each binomial, I guess, as f of x and g?
that's what I'm about to do, sister. H of x is equal to x squared plus 6x. I'm just rewriting this times 3x plus 5. I notice that here I am multiplying two functions. We can use the product rule. F of x is x squared plus 6x. G of x is 3x plus 5. The product rule says that the derivative of f times g is f prime g plus g prime f, and therefore I need the derivative of each one of these things. The derivative of f of x is 2x plus 6. The derivative of g of x is 3. And now we just use the formula. It's like cross multiplying. F prime times g plus g prime times f. F prime g plus g prime f. We'll just write this under. F prime is 2x plus 6 times g, which is 3x plus 5, plus g prime is 3 times x squared plus 6x. And of course, these are supposed to be the same. Okay, if you simplify. Okay. So using the power rule directly by FOILing, using the product rule. Of course, I put up this fantastic function earlier, x times the sine of x. I clearly will want to know how fast that's changing at power over 2, right? I want to know how fast x sine of x is changing at 15 power over 2 or 3 power over 4, right? In order to do that, I will need the product rule, right? Because I'm multiplying one function times another one. So this is why it's going to be useful, right? So whenever you come across two functions and you're multiplying, you can always end up using the product rule to do that. Questions on that? at this point, full disclosure, we don't have any other functions to multiply, right? So using the product rule is not that useful. I do want to introduce one other function that we've been using before, and that is the exponential function. So it's going to be f of x. We're in calculus, and so we care about a particular base. It's e, that's right. F of x is e to the x. This is, of course, opposed to f of x, or I should say g of x, is equal to 10 to the x, right? Where h of x is 2 to the x. Now, you all have had pre-calculus, and so pre-calculus was all about functions. I mean, you just went through, learned about polynomials, quadratics, trinomials, higher order degree polynomials. Then you went to exponentials, logs. You talked about trig functions, right? We learned that with linear functions, obviously linear functions are really applicable to real life because tons of things change at a linear rate, right? Exponential functions are useful where? Where would you use exponential functions to model what?
Population growth.
For population growth, for sure, right? So what happens now that we're using exponential functions all the time when we go to YouTube? What happens on YouTube that's like an exponential growth? Go ahead. Views, right? So that's what makes something viral, right? Is that the growth, at least it looks locally, looks like that it's exploding. And so our general notion of exponential functions is like, boom, right? And oh my goodness, it's obvious that if we are talking about how fast that thing's moving, then it's clearly a calculus question, right? Right? This is clearly a calculus question. And so whatever the derivative of the exponential is, it looks like it's going to be really big, right? That the derivative, it gets steeper and steeper and steeper. The slope of the tangent line there looks bigger and bigger and bigger, right? Now, I'm being biased, of course, right? You have an element that obviously can also decay, right? So that's a legitimate exponential function too, right? So that's 1/2 to the x power. That's perfectly okay, right? Moore's law says that, in the 80s he said this, he says that over time processing power is going to double and the space required to hold that power is going to cut in half, right? So that in the 70s we had huge mainframes of computers that had processing power that was less than this thing. So all of that space decreased to this and all the power to hold it increased, right? So in the 90s I was loving those computers which had 64 megabytes on the hard drive. Right? And so, of course, we know that 64 is not special. I mean, 64 is kind of special. It's a power of 2, right? So that because computers are programmed in zeros and ones, then everything is in powers of 2 in terms of the space. So that when they say 1 gig, of course, they're not talking about 1 gig. They're talking about 1,024 megabytes because it's a power of 2. Right. And so exponential functions are everywhere, okay? Particularly when you're talking about finance, all interest rates. Interest is about exponential functions and so forth. But you learned all of that stuff. So in pre-calc, we had a definition of E. What was it? E is equal to 2.7 2.73 roughly, right? So you know what I'm about to do to this equal sign. Oh, for sure. Right. Right. Okay, good. You know me enough by now that, of course, I wouldn't accept this as the definition, right? So, anyone see the limit definition in pre-calc?
Limit is
Okay, so it's the limit as n tends to infinity of something. Did we all do? No, did we all do compound interest?
yeah.
You did compound interest in algebra. Okay, great. So P equals,
Initial
I should say A equals, right? A equals P times 1 plus
R
R over N to the NT power. Yes, you remember? That look familiar? Okay, excellent. What I want to do is this. I'm going to take $1. I'm going to give you an interest rate of 100%. Oh, yeah. I'm going to compound it every moment. Every moment. Just compound. Every instant. Just compound. Go ahead. So continuously. So that's what continuously means, right? So that you compound every moment. So if you do that, then did no one ask where this came from? But how does somebody? So I'm loving this. How does someone introduce this and we don't ask where did that come from? So it comes from the fact that to go from this formula to this formula, what do we do to n? We let n go to infinity. We let n go to infinity. And so if we did that, right? If we let n go to infinity, then it kind of tells us where e came from. Right? So e is actually the limit as n tends to infinity of 1 plus 1 over n to the n power. That's what e is. Right. And again, it's hinted at by the fact that PERT just shows up when you let n go to infinity. Right? So that means that e and this limit are related, and it's by this. And in general, e to the r, if this is an r, then that's an r. Okay, so e to the r is the limit as n goes to infinity. Okay. So e to the first is the limit as n tends to infinity of 1 plus 1 over n to the n power. Okay? So that's the pre-calculus definition. Please, go ahead.
How does e have a value if it goes if it's from 1 to infinity? Or 1 raised to infinity?
That's a great question. Let's talk about that. So this is an indeterminate form, right? So she's saying, look, we got some problems. N is positive. 1 plus 1 over n is bigger than 1, right? 1 plus 1 over n is bigger than 1, yes? Yes. I got something bigger than 1 and raising it to the infinity power. That should be infinite. Well, wait. What does 1 over n go to? 0. Oh, so 1 plus 1 over n goes to 1. Well, this thing's going to 1, and I got 1 to the infinity, that's 1. Right? So you're correct. There is this battle between those two things, right? That we got the thing inside going to 1, the thing outside is going to infinity, but the thing inside is always bigger than 1. So what's important, again, is a rate issue that this, and this are the same. And so this is going to 1 at the same rate as this is going to infinity, and so it balances out to some number in between. Is that okay? That's the street version. I will, of course, prove this and say it in more technical terms later, but this is called an indeterminate form, right? And so that's the reason. So it balances out. So the way that you show this mathematically, I'll give you the street version of that, is that you look at this sequence of numbers and you say, oh, I know, we first show that this thing's always less than 3. Okay, so you can show that 1 plus 1 over n to the n power for any n is less than 3. And then you show that it's increasing the sequence. And so if I have something that's increasing, if I have a sequence that's increasing, but it's always under 3, the question is, does it have a limit? It's going up, but it's always under 3. Does it have a limit? It does. An increasing bounded sequence always has to go to something. If you're always going up, but you have to stay under this number, then you just can't. You have to go to something. And so that means that this limit exists, and whatever it is, we call it that number, e. That's what. So we just show that this sequence is increasing and bounded. That means it has to go to some number, and whatever that number is, we give it the letter e. E is in honor of probably the greatest mathematician who ever lived, Euler. Go ahead.
Oh, how do you know it's less than 3?
That will require an hour or so. Yes, yeah. So we can talk about that, yeah, at lunch or something. Yeah. Okay. Other questions about this? I want to get to the point. We want to take the derivative of e to the x. And for that, oh my goodness, we're going to cheat. Whew, my goodness. So f prime of x, the claim is that f prime of x is equal to e to the x. Now, I'm going to start the cheating early. Okay. So I talked about the pre-calculus definition. I'm going to give you the calculus definition of e. Okay. So e is important in calculus because 2 to the x looks like this. E to the x looks like this, right? 3 to the x looks worse, right? So they all go through. Wait, I have decimals. What am I doing? Right? Why am I wasting my time, right? Oh. We can just cut these out, right? Okay. So e to the x, we call it the exponential function. There it is. 2 to the x is that one. 3 to the x is that one, right? Let's zoom in. Which is which? You can see, right? That the before 0, they switch the order of greatness, right? We know, obviously, e is between 2 and 3. So as you move to the right, 3 to the x is just going to end up crushing everything, right? Because it's the bigger base, right? But before 0 is the complete opposite. It's like the power is now negative and you flip it, right? Before 0, x is negative, x is the exponent, and so you're flipping everything. And that's why the order changes. Why is e special to us, right? There's something about the slope at 1. The slope at 1 is 1. That's why we like it, right? When we look at the slope of 2 to the x at 0, it's not 1. The slope of 3 to the x at 0, that's not 1. E is the only base where the slope of the tangent line at 0 is 1. Right? So that e is important in the calculus sense, and we call it the natural base because of that calculus concept. Okay? And so that motivates a definition of e that again will seem like cheating. The calculus definition of e is that e is the unique number for which the limit as h tends to 0 of e to the h minus 1 over h is equal to 1. No other number can do that except for one number, and that number we're calling e. That is the calculus definition. So, okay, this is good. So, of course, the great skeptic comes in and says, yo, I have this other definition of E. You gave me this one. Are they the same? The answer is yes, right? So it's very difficult to prove that if E satisfies this, then E satisfies that limit. And if E satisfies that limit, then E satisfies this, right? But that's true. It would take another 2 or 3 hours to show that, but that is true. And you can look up that proof. So the definitions are equivalent. And so now the derivative of e to the x is e to the x. We'll show that tomorrow. Right? We'll end there and show that, and that's the only base where that happens. Okay. We'll talk about the exponential function, prove the quotient rule, or I'll give it as extra credit, and we'll move forward.